So this class is about the orthogonality property of the mode shape. So last class we have studied about the how to draw the mode shape. That is we have discussed that the mode shape vector is represented phi. So phi is equal to, we will be getting, if it is a two value problem, we will be getting like this: 1 some value 1.5, then 1 minus 1.7, like that, or it may be positive, like that. So we have discussed how to calculate this in a 2 degree of freedom MDF system. Now we need to study about the 3 degree of freedom, but before that we need to study about the orthogonality property. So let us look into that. So for that, here let us consider a displacement vector. That is, I am representing this displacement vector u of t can be written as a product of the model shape and the model coordinate. That is, if I am having a SDF system like this, m1 followed by m2, then it will be having x1 and x2. Then I will be finding out phi. Phi, it is a model coordinates. So phi will be for a 2, here it will be like this. That is, it will be phi matrix will be, I can write like that, is phi 1 1, phi 1 2, phi 1 2 1, phi 2 2, like that I can write. So for each coordinate, if I am considering for the m1, this is for m1 and this is like that. So here the total displacement can be written as phi n. Phi n is this vector, generalized vector, phi n into xt. Xt is so the model coordinate varies with the time, whereas mode shape does not. Here you can see this mode shape, it is not varying with time, it is constant. But what is varying with time? The model coordinates will be varying with time. Okay, that is time dependent. Model coordinate means x of t, this will be varying. So if I am multiplying this x of t with phi of t, I will be getting u. That is, for example, if it is having a vibration here, it will be moving by a distance x1, this also by x2. So here the total displacement will be, for example, if I am considering this one, it will be phi 1 1 into x1 plus phi 1 2 into x2, like that. Like that, for any degree of freedom I can write like this. That is, the displacement vector is equal to the model coordinate into mode shape vector. This is mode shape vector. Okay. Now you can see in a free vibration analysis, the model coordinate varies like a simple harmonic or a with the frequency equal to natural frequency. So this equation I think you all have seen, that is x of t is equal to, this is a starting equation where we will be writing x of t is equal to a cos omega t plus b sin omega t. That is, now here we know that, but here we know that this is a equation x of t. So I am substituting, instead of here in this equation I will be getting phi of t into a cos omega t plus b sin omega t. Now I am considering a this equation, we all know what is this equation, that is for a undamped SDOF system equation. So here I am substituting this, you can see here, that is, here I am having x of t, here I am having m, instead of u I can, here you can see m phi n into minus omega square. Why how this omega square have come? Because we have to take the double integral. So this is equal to 0. By rearranging, I will be getting an equation like this: minus m phi n omega square plus k phi n is equal to 0. This phi n is a matrix only, that is a model matrix. Okay, mode shape matrix. So this is phi not into n. This is a single term. So from this equation, how can I write? This x cannot be 0. It will not be 0, but this term can be 0. So I can rearrange this as k into phi n is equal to m into phi n into omega square. Now you have to understand that these are vectors, these are matrices, therefore I cannot cancel this. So this is my equation, k into phi n is equal to m into. Now we can see here This is called matrix eigenvalue problem, and the matrix K and M are known. Then we can find out omega n and omega phi n. So here you can see I am just rearranging this. I will be getting K phi n minus omega n into M into phi n is equal to 0. From in here phi n can be taken as outside as a common. Now again this equation can be satisfied by either phi n is equal to 0 or the determinant this can be 0. So I am taking this. So this determinant is a polynomial of order n in terms of phi n square, and this is the equation is known as characteristics equation. This one we have studied earlier also. We have studied this equation. So it has n real and positive roots of phi n square because matrices K and M are symmetric and opposite. K and M are symmetric and a positive determinant. Now the n roots of the omega square are known as eigenvalues. So these things I think we discussed in the last class, and they are also known as the natural frequencies. Okay, for the value of omega square, phi n can be solved from the equation K minus omega n square into M into phi n is equal to 0. But they are not unique because many vectors obtained from scaling of solution will also satisfy the equation. So the shape of the vector phi n, this is known as natural mode of vibration or mode shape. So that is the reason it is known as mode shape. Okay, now you just, so here this is how the phi n will be. This is how I have just started for a this phi. This is known as model matrix. Phi is the model matrix, and this here I am taking it as omega square, that is capital omega square is equal to omega 1. These one will be the natural frequencies for a n degree of freedom. Okay, now I can write that is K into phi n is equal to omega square into M into phi n. Now here this can be written as this phi n is again a matrix. I can write like this, phi into it, that is can be written in a matrix form. Now let us look into what is orthogonality property. Orthogonality property is this one, that is you have to listen what is written here, that is phi transpose n into K into phi r is equal to 0, and also phi transpose n into M into phi r is equal to 0. What is this? That is, if I am having a matrix, phi matrix like this, okay, this is phi 1 1, this is phi 1 2, this is phi 1, like that I can write. So this one I am taking it as phi n or phi a, this is phi b, this values. So if I am taking a transpose of a, this one will be for M1. So phi transpose, phi a transpose K into phi b is equal to 0. Similarly I can in other words how can I write phi b transpose K into phi a is equal to 0. Similarly for M also I can write. Now how we can prove that? This will be asked most of the exams, that is I can prove that is, okay, this is a general equation that I know. Okay, that is I am multiplying it with the phi r transpose. You can see in both the sides I am multiplying. Above is a scalar, so we can transpose the right hand side. I am taking the transpose of the right hand side. So here phi, I am taking the transpose. How will I can write phi transpose K phi r plus omega into phi n transpose M into phi r. So I am just taking the transpose. Suppose we start from the rth node. Now here I have written phi. This was the first equation. Okay, this was my first equation. Now so I have got one equation. I am less marking as 2. Now if I am writing, I can, here I am taking the nth node. Nth node means this these values. One row values it is known as node. One column value it is known as node. That is to be clear, you can see here. You see this is phi a, this is phi r, or I can take it as phi a or phi b, like that. It depends. So here you can see I'm writing this sorry. Okay, so this is my equation. So I am just writing I am taking the rth node. So how can I write? Now I am again pre-multiplying it with the other one, that is phi transpose n k phi r is equal to omega r square. The same equation. So from these two equations I can write. So subtract these equations. This is first second equation and this is first equation. So by subtracting and taking, I will be getting this one. Phi transpose m phi r is equal to 0. But how can, in this, can this be 0? This cannot be 0. This cannot be 0. So only this term can be 0. So this is, I have proved the orthogonality property. Okay. Now the orthogonality condition implies that the matrices K is equal to phi transpose K into phi, that is M is equal to, so are diagonal with the diagonal, that is these matrices will be diagonal because K and M are positive definite, so Kn and Mn will be diagonal. So while doing some problem it will be more clear to you. So this is a way, this is known as the orthogonality property. So what is orthogonality property? That is phi transpose phi A transpose, that is A is the eighth first node, into K into phi transpose B, phi B is equal to 0. Similarly, phi transpose A into M into phi B is equal to 0. So likewise I can take it. Now that is normalization of modes. That is a eigenvalue multiplied by a scalar scaling factor is also eigenvalue value correspond to same eigenvalue. Therefore only the shape mode is essential. So we only, that means that only the shape mode is 5. A mode can be scaled without changing the shape. This is called a normalization. Sometimes the mode shape vector is also called the largest element of unity. Now in computer programming we can use this, so we will discuss on this later. So this is a very short video that will explain the orthogonality property of the eigenvalue problem.